James doesn't want to do the claim game until he's seen me do it, and I fully understand that. So we'll be discussing that, but I am going to make a homework assignment today. It will go up on Blackboard. I'll post an announcement about it. I mean, you can shut those off if they irritate you, right?
What?
Announcements. And they, if you would prefer just to go look yourself and see if the homework is posted, but sometimes it's useful to sort of nudge everyone and say, hey, the homework is posted. So I'll see if you guys start complaining to me about it, then I'll quit. So okay. All right. So today we're going to start doing a little bit more of the fun stuff and the trickier stuff. We're going to discuss initially negation. I talked a little bit about that. So last time we discussed and we know that when we negate that, we get an or and vice versa. But of course, you're also negating the other statements that are being connected by this conjunction, right? So, I mean, you don't just go through and flip the ands to the ors. And speaking of that, if you treat negating things and logic and proofs as some sort of algorithm that you need to learn, like, okay, I can negate this if I just go through and I turn the ors to the ands and I move such that's around and all that, you're going to have a lot of trouble, okay? It's like trying to learn to speak, being told, well, you have to have a verb, you have to have a noun. I mean, you don't think about that stuff when you talk, right? I mean, I'm talking right now and I'm not thinking about what's a verb and what's a noun and how to construct my sentences. I'm just thinking of this idea that I want to talk to you about how you talk about things, and then I talk about it, right? Okay, so you have to be the same way with logic. You're basically relearning your language and you're restricting what things mean to very precise things, and you can't use them as flexibly as you used to. And you know that already, right? I mean, continuous, right? You can't just use that, like a continuous stream of thoughts, okay? There are people, they're called crackpots, who like to, say they've solved, the unified field theory, and they do exactly that. They take the words from physics or mathematics and they use them in nice spiritual ways, but it doesn't actually solve anything, okay? And you will have the same trouble if you don't learn precisely how to use the language. Okay, so we have and or, and when we negate them, they go back and forth, and then we had this sort of super and, which is called for all, and that just means everything. So these things will mean what they mean in English. We're not really, at this point, giving these things new meanings. What we're doing is forcing you to think about them in a very precise and exact way. And when you negate for all, you get a there exist. Now, when you're doing this and you're negating something and you start to feel a little bit queasy about it, then these can provide useful checks, right? You can go back and you can check, well, did my ands get reversed to ors where they're supposed to, okay? Because when you have a big complicated statement like an if-then, as we'll see later, you might not be negating part of it. And in that part of the and doesn't change to an or, only the parts that you're negating, okay? So this is why you can't sort of have some kind of algorithm. Many of you could probably program a computer to negate statements, but there'd be a huge, huge, huge list of exceptions and who knows what else, right? Because the English language is quirky, okay, and not designed for logic, as I said. We can use it for logic, but we have to be careful. Okay, and then we had if-then. And so this part here is the hypothesis, and this part here is the conclusion. I'll say some more about some other constructions involving if-then statements at the end, but this, when you negate it, the hypothesis is SIS. I need two is's there. True, but conclusion is false. Okay, that's when you negate it. Now, and again, here's where so let's just say often an if-then is a for all statement, which you would negate as what? There exists, okay? And why is this true? It's often a for all statement, and we'll do some examples, concrete examples, which I know everyone likes to see. But remember, what does if means? If the hypothesis means, in all circumstances when this is true, okay? So there I just used the word all right? And so very often you can think of an if-then statement as being a for-all statement, which you would then negate by showing that there exists something that satisfies a hypothesis but doesn't satisfy the conclusion. Okay? And again, I can tell you these things all day, but the best thing to do is for me to actually work through some with you here, and then for you, especially important, to go through and work some of these. All right? And work the same ones that I'm working, and the examples in the book and whatever, and then start working on your own, right? Well, not on your own, without me, hopefully, but maybe together. But even then, make sure you don't rely too heavily on everyone else. So any questions at this point? Okay. So let's just do something. Okay, so there exists some n, an element of n. So, and I'll introduce this now. It's a good time, right? This is just what you learned, the natural numbers. That you learned about ages ago, and I don't. Some people like to put 0 in there. I don't. Most people don't. So anyway, that's the natural numbers. 1, 2, 3, 4, and so on. And this is interesting. This is actually a font now. It's called Blackboard Bold. And mathematicians are responsible for this because this is the way we used to do bold on the blackboard, just the way I did now, to represent bold that's in textbooks. But now it actually is a font called Blackboard Bold, and you will see it in some textbooks, including I think maybe in mine. Okay. Okay. So there exists some n element of n. I don't know. Let's just do something simple to start with, such that n is less than 2. All right. First question, is this true or not, given what you know? We're not going to prove anything along these lines for a while because we don't even really know what the natural numbers are yet. But is it true or not?
Yes.
Yes, why is it true? 1. Okay, 1 satisfies this, so it is definitely a true statement. Okay? But if you weren't sure about this, or since we're practicing negating, let's go ahead and negate this thing. Now, I'll go ahead and circle it now. Something that will give some of you some trouble is this. Okay? And I will, read these negations where there'll be a such that stuck in a weird place. Okay? Because you're not sure what to do with it. And the reason you're not sure what to do with it is that you're trying to think about it as an algorithm, that I got to change these things, and then you just stick the such that in there somewhere. But if you actually go read your statement, it's gibberish because there's this such that in there that doesn't do anything, okay? And so what is a such that? A such that is just a way to describe the properties of something you've referred to previously, okay? So, there exists some n element of such that n is less than 2, okay? Right? So this is referring to the n, right here. And when you negate things, sometimes it just goes away or it moves around, and you've got to not try to think about, oh, where do I move it, okay? You've got to think about this, try to comprehend the statement, and remember the statement could be true or false, but you can still understand it, right? You can still understand it, and once you understand it, it will make it a little bit easier to negate it. So try not to make this a formal process. Okay, so all right, so we agree to this too because 1 is a natural number. Okay, but we want to go ahead and negate this. Okay, so how do we? What kind of a statement? When you negate something, you step back and look at the big picture and you ask what kind of a statement is. So overall, what kind of a statement is this? Not the negation. The statement that we had there, first of all, is what? Basically there exists statement, right? That's the key thing. And so what it's going to be when we negate it is a for all. Okay, so this says there exists some n. So when we negate it, it's going to be every n doesn't have that property. Okay, this says there is some n with that property. If we negate it, it means for all n, that property is not true. Okay, so and again, you're not going to. And again, there are these questions. Well, I'm negating, so why don't I negate the element of, because that's not what you're discussing here, right? This says there is someone with this property, being an n, that also has this property. And if you're going to negate it, that has to mean that everything with this property, not with the negated property, but everything with this property has to not have that property. Now, sometimes you'll find that when I talk about things too much, it's worse, okay? And that's because, again, you may have had an inkling of understanding of this, and then when I try to explain it, it just kind of wipes out your understanding, okay? But on the other hand, it is planting something there for, I hope for future reference, okay? When you sit down and try to parse this again. So we're not going to negate the n element of n yet, okay? At all, right? So for all n an element of n, and there's no such that anymore.
N is greater than 2.
Greater than equal to 2. Exactly. We did that at the end of class last time, right? You got to get that extra equal to. Okay. Questions about this? By the way, I could state this with a such that here. How could I put a such that in there if I just felt so inclined?
Such that n is greater than or equal to.
No, we wouldn't want it there.
There is no n element.
Okay, we want to be careful about that because we don't, you're right, but we don't want to, so one of the things that I'm going to say later is we want to completely negate things, okay? And so we don't want to have, it is not true that, or there is no, right? Because you want to, you can't, that's not useful because all you've done is you've put a no or not in there, but you're not understanding what it means any better, okay? So that's why we want to sort of completely negate it like this. But there is a place where we could stick a such that in there and make this statement a little bit longer and change slightly the way it's done. And how is anybody know what we...
N such that.
Yes, exactly. We could also say for all n such that n an element of n bigger than or equal to 2. It means the same thing. And sometimes it's better to expand a little bit like this when you state it, okay? So I wasn't trying to be tricky there. I was just pointing out that you could make it that way too. And then you would have a such that, but you see it's sort of moved, okay? And that's just because this particular statement is often written without a such that in front of it. All right, any questions about that one? Okay, yes.
So on the such that thing,
Yes.
what's wrong if you, what does it do if you stick it next to?
So you want to put a,
Yeah, just.
you want to put a, okay, such that, and now read it, okay?
N is an element of n such that n is greater.
There's no verb.
Yeah, okay. Right, no verb.
Now this could be a part of something. For example, I mean, no, let's forget this. Let me erase this, okay? So a construction like this might be, let's turn this into a new statement, which we will then negate. For all n such that n is bigger than or equal to 2, n squared equals n. So let's negate this one. Negate it for, okay, so, right? Okay, true or false, first of all? Right. Okay, it's false. In fact, it's not true for anything in natural numbers except, of course, 1. Okay. Which we've excluded by this. That's why I put it up there. Okay, right? So this is a false statement. But so when we negate it, it should be a true statement. So that's another thing you can do, right? If you first start by understanding the statement, and there's at least one that you can't understand, okay, I guarantee you in the homework, okay, so then you'll just have to do it formally. But anyway, if you at least understand the statement, then when you get done, you can read it and say, do I understand this and do I understand, and not just understand, but do you know whether it's true or false? Then when you negate it, you should also understand it and understand why it's not true if the original was true, or why the negation is true if the original was false. Okay? This is a false statement, so when we negate it, we better get something that's true. Okay, so overall, what kind of a statement is this? It's a for all, so how does it get negated? There exist. Now what? Do we take n?
Exists an n element of the natural numbers.
Yes, so we do not negate this thing. We do not say it's not in there because again, we're talking about all n's in the natural numbers. If we throw it out, then it doesn't even apply to the original statement. Okay? So for all there, so now there exists an n, an element of and now
Such that there is an n less than 2.
okay, careful.
Such that 4 n
for n less than 2.
Wait, we're talking about one n here, okay?
That is greater than or equal to 2.
Yes, we have to still make it bigger than or equal to 2 because here is the description of the n's we're talking about. We're still talking about this kind of n. Okay, where will work, but let's stick with the phrase the troublesome phrase. Okay, where is perfectly good too. And would work, but and would work also. Where would work, and this is why I tell you that this English language is flexible, and you just have to get a sense for it, right? And part of that's going to be by reading things. Okay, let's go ahead and use our such that. So we got 2 such that's. So that's why where would have been nicer, right? Okay, because then we're not, math writing can often be, when you're writing a proof, it's usually, pretty boring, construction, right? Because you want to be simple, because it's hard enough, without having some big complicated sentence, right? Okay, we have 2 such that's. We could use where or with the property that or something like that. Okay, and now what do we conclude with?
N squared does not equal n.
Okay, now let's just be thorough here, okay? Let's go ahead and say what that means, because that's not equal to, and we don't like nots in here, okay? So what does that become? Okay, but we really need to expand what you said, because I can't just such that greater than or less than, okay? That doesn't make sense.
That n squared is greater than.
You stopped.
Greater than n.
Or, exactly, or
n squared less than
n squared less than n. Okay, that's totally and completely negated. Now, as was previously brought out, does everybody understand why this is completely now negated? Because we've gotten rid of all knots in there. That can't always happen, and sometimes you want to do things in stages and put this is not true, and then you want to expand that, right? It's not always easy to start with something like this and just blast out the negation, although you should be able to do that at some point, right? It's like being able to, FOIL quickly when in algebra, right? You remember what that was, right? Multiply 2, right? So this is a skill that you have to develop, all right? And as someone pointed out, you could use where there, and then it at least avoids the repetition, or with the property that, which is longer, but sometimes you just, again, you are writing something that you're hoping somebody will read and comprehend and not, not get completely bored out of their skull with. So, okay, so. Questions about that? Yes?
Would you have been okay with saying there exists an n element of n that is greater than or equal to 2?
Yes.
And then you want to switch that? Okay.
Yes. Or you could say so there are lots of ways to do this, and that's partly why you have to get a sense for it, right? Because when all of you turn these negations in, most of them will be a little different from each other, and right. So so what you're doing when you bring this up, and I'm going to bring your names in at some point and start learning them, right? So I know Sarah's name because I know her sister, but anyway, the rest of you, I guess it's going to take a little while. Okay. So, but anyway, you've got to understand it, and then it doesn't matter that it's a little different, from somebody else's, right? Yes.
Can you stick an equation in there, like n squared minus n, right there, n squared minus n, instead of the or? Because it doesn't equal 0.
Well, you got to have these 2 options in there, whatever you do. And there might be, right? You got to have those 2 options as possibilities. And there are going to be different mathematical ways to describe that. But as long as they're equivalent to these 2 options, then you're okay. But I think this is probably the simplest thing to do. You could change this to n squared minus n is bigger than 0 if you wanted to, right? But that's just going to sort of confuse the issue a little bit. It might be useful in a proof to grab and say, oh, and this means that n squared minus n is bigger than 0, and now I can do this and this and this, okay? But for just the purpose of negating right now, we'll just leave it at this. true. You certainly may want to use a different formulation of that depending on what you're doing. And that's something we'll get into a little bit later. Okay. So how about if n is greater than 5, then there exists some epsilon bigger than 0 such that n plus epsilon is less than 6. True or false? Something is false. The only way, really, I mean, in here, and to really show that it's false is to find an explicit counterexample. Okay, so this is a statement about n is bigger than 5. So what would be an explicit n that shows that this is a false statement? 6. Okay, because you see, remember, epsilon is positive, and we need n plus epsilon, so n plus a positive thing, to be less than 6. So if n is equal to 6 or anything bigger, then we're in trouble, right? Okay, so this is a false statement.
Do you always have to include the definition of, I mean, n is assumed to be a natural number. Yeah, that's what I was.
Okay, that's a good point. And does it need to be a natural number in this case? It's not stated, so n could be a real number. As soon as you see an inequality like that, then that tells you, at least for purposes of this class and most math classes, that n has to at least be a real number. I mean, there's no ordering on complex numbers, and you guys are probably not familiar with other kinds of numbers at this stage. Okay. It would be a good idea to specify what it is, I agree. But anyway, for purposes of negating, we'll just go ahead and do it. It is false whether it's real or whether it's a natural number, right? Okay. Because 6 is both a real number and natural number. Sorry?
I said if it was like 5.5 and 0.1, that would satisfy both of those.
Yes?
Yeah,
Yes? So what's the matter with that?
it's true.
That makes it true.
Yes, but if means in every situation when the,
Okay, yeah.
right?
Yeah.
Okay, that's this is a situation where you want to think of this as a for all statement, right? This really is a for all n bigger than 5. Yes?
So, in order for that statement to be true, n would have to be limited to less than 6.
Yes. So if you change this to be if n is less than 6, what about less than or equal to 6?
No, because you have equal to.
Right. If it's equal to 6, you're in trouble. Okay? And so we'll actually understand, I mean, you have some sense for why this would be true. This is a slight digression, but it's an important one, I guess, right? Here's 6, right? You have some sense, and let's suppose n is just a real number, just to make things easy. You have some sense for no matter how close you get to 6, you can get a little epsilon that you can add. Remember, this says there exists some epsilon, so you're allowed to choose it, right? And so you know sort of from what you've done in calculus and so on that no matter how close you get to 6, you can find a little epsilon so that if you add, how small do you have to make epsilon?
You make it as small as you can get to.
Well, but you can be very precise about how small you can make it if you want to be clear, right? How small are you guaranteed? What's a guaranteed number that if you
6
make
minus n.
6 minus n. If you make epsilon smaller than 6 minus n, then when you add it to n, you're still less than 6. Okay, so we've just done a proof from later in the class, all right? You don't need to write it down, but anyway, that's the kind of stuff we'll be doing later. And that's why you have to be able to think about these things carefully, okay? So it's absolutely true if this were n less than 6, then the statement would be true. Okay, but since we're saying n bigger than 5, it's true in some cases, and it's not true in other cases, so it's, as a statement, it's not true, right? I should say it's true. This is, the conclusion is true for some n's, but it's not true for all n's that satisfy this property. So as a statement, it is false. Okay? So now let's negate this guy. And you can use your, the way you disproved it as a model for what to do. So what's going to be my opening phrase? And very often when you prove and you negate things, you think about the starting point, okay? So this is an if-then statement, but it's really what kind of statement in this case? It's really a for all. So what am I going to start with in this case? There exists some n bigger than 5 here I take out my such that stamp. Okay, such that, which also means with the property that or something like that. Such that, now what?
Some sigma greater than 0.
That's an epsilon, but
Or epsilon.
but there's a worse problem. I don't care if you mislabel the Greek letters, but there was a worse problem with what you said. And what? Sorry.
For some.
Worse than that.
There exists for become for all.
Becomes a for all. Right? Because we're saying if there is an n bigger than 5, if n is bigger than 5, then there exists something. And so remember, we're negating the conclusion, right? Remember, the negation of an if-then statement is the hypothesis is true, the conclusion is false. So once we get past the then part, we got to be in negation mode. So when you said some, of course, what should it actually be? For all, right? We have a sum, or there exists, right? And remember, after the end part, we're now in negation, right? We got the hypothesis is true. There exists some n bigger than 5, so the hypothesis is satisfied. But, and we don't use but really in proofs, it's a little risky, okay? But just means and, okay, right? So such that what? For all. Okay, now, do we say epsilon less than or equal to 0? No, because if you think about, again, the original understanding of this, you're adding a positive epsilon. So we're still, we're not negating this because the such that, the original there exists is about these, right? So for all epsilon bigger than 0, yes. Okay, and now having negated it, you can stop and think about it for a minute, okay? So someone said that 6 is a counterexample to this, right? So let's see, is this true for 6? Well, yes, 6 is bigger than 5, and for all epsilon bigger than 0, n plus epsilon is bigger than or equal to 6. Actually, we can do more than that, right? It's actually bigger than 6, because epsilon is bigger than 0. So then, having done all that, you should be reasonably confident that you've done this correctly. And so this is why I tell you, you can't just think of this as there's some algorithm you go through and you change that to bigger than or equal to, less than or equal to, and that's for all. You'll get gibberish. Right? So you got to think about it. Understand it if possible. If not possible, then think about the structure of it and what you have to do with it.
Why can you get rid of the equal?
Where?
Did you say n plus epsilon?
No, I said in the specific.
No, right there. Did you
Yes.
say that greater than or equal could be? It has
In the case of 6,
yeah.
it actually that special case. I'm not talking about in the negation. Okay. This is the correct negation of the statement.
Okay. Yeah.
But in the specific case of 6, if you add a positive epsilon to it, it's actually going to be bigger than 6. Yes.
Also, just as an aside, we still have a false statement, since we can.
No, this is a true statement.
Okay.
Because 6 works. That's what we just checked. And it definitely wouldn't be a side because you don't want to start with a false statement, negate it, and end up with a false statement. Okay, so this is, and there are lots of such ends, right? 7, 8, 53.2, 10 pi.
We just need one there.
Yes, to disprove a statement, and this is a nice thing, right? So you should be happy when you have to disprove something, although it's not always easy. But to disprove a statement, you need one and only one counterexample. One thing that shows it's false. Doesn't matter if there are things for which it's true. If it's a for all statement or an if then statement, you just need one thing, right, for which it doesn't work. Can't prove things that way unless you have finitely many things, right? Or if you've got one thing, then you can prove it about that one thing. But okay, yes.
I know we kind of touched on this, but
Go
are
ahead.
we still assuming n is a natural number? Because in the case of, let's say, 5.5 is n and epsilon is 0.1.
Yes.
Only 5.6.
But we're back in the mode of there are statements for which there are n's for which the conclusion is true.
But for the negation to be true, it just has to be, that statement just has to be.
There just has to exist one for the negation.
Okay.
So there are also ones for which, right? Remember, it's very, and these are, and you say we touched on this. This is extremely important. I mean, when these questions arise, what we're discussing right now is of fundamental importance in your thinking. Okay, to understand, to think about, well, why isn't 5.5 a problem here? Okay, and the point is that this is a statement. There exists some n with this property. It doesn't matter. There's some other ones that don't have the property. Okay, and this is a very common mistake, and I want to say something about answering, saying wrong things in class, okay, or making mistakes out loud. Maybe it's a little bit uncomfortable, but I can tell you what, the best way to learn something is to make an incorrect statement in class, okay? That's why we do the claim game, okay? Because it will stick with you, right? And so don't be afraid, and nobody's going to get mad at you, okay? In fact, probably half the rest of the class is thinking the same thought. And you were the one who was nice enough to open your mouth and, and take the fall for it, okay? And so I'll try to make it as nice as possible to point out when something is incorrect, but you're doing a great service to the rest of the class when you ask a question about something like that, okay? Even if it's something that we've already discussed, because it takes a while for this to sink in. And this is not going to be easy, right? It's not going to be easy, and you need to thrash through all this now. Okay? Everybody resolved on this, because we're going to move on a little bit. This is about as complicated as your homework is going to get. And so, if you can handle something like this, you should be fine in the homework. Okay? Because we got to move on to set theory. Oh, before we do that, there are a couple more constructs. These are just basically definition things, and you'll have to do some of them, but it's no worse than negating. Okay, so if we have an if-then statement, there are some things we can do to it. There's the converse, which is if B, then A. Now, one of the things that human beings are somehow wired to do is occasionally get these two statements mixed up, okay? This is a favorite tool of con men and politicians and whoever else, right? If you want to convince somebody of something that, either you don't know for sure is true or is not true or whatever, or you think it's true even though it's not, somehow make a clever use of the converse statement, okay? Now, in obvious cases, you understand that these two things are different, okay? One could be true and the other false. They could both be true. They could both be false. There's no connection between these two in general. All right? So, for example, if I jump off, a cliff in the Grand Canyon, I will die. Now, let's not argue about whether or not that's necessarily true, okay? Let's just take for granted that it's true, okay? The converse of that is, if I die, then I've jumped off a cliff in the Grand Canyon.
Yeah.
Okay? So, even if the first one is true, okay, and maybe somebody survived it, I don't know, but even if the first one is true, the second one definitely isn't, because there are lots of ways to die, okay? Not to be gruesome or anything, but, that's just the first thing that popped into my head. Maybe because I'm too busy or something, I don't know, okay. All right, but does everybody see that these things are independent? And it's a useful thing to look in the newspapers, turn on a talk show or something, and listen to how often somebody does this, right? Presents the converse, which is true, but that's not really what they're trying to get you to agree with, all right? There's also the contrapositive. So this is like super easy. I mean, I don't know if I asked you to do this, but if I do in the homework, I don't remember. I'm sorry, because it's basically you just changed A and B in the statement. Okay, so it's totally boring. But something called the contrapositive. So this is independent of if A, then B. It's independent of it. The contrapositive, for the contrapositive, you reverse A and B and you negate them both. Okay, so this is if not B, then not A. This is equivalent to if A, then B. Okay, so this is true precisely when the original one is true and vice versa. Now, you can see this through truth tables if you want, okay? I mean, this is just one of those things, or you can just think about it, which I think is preferable because somehow I think the brain likes to latch on to concrete things, and truth tables ultimately aren't very useful. So let's just do the example I just did before. So if I jump off a cliff in the Grand Canyon, then I will die. Okay, what's the contrapositive? If I didn't die, then I didn't jump off a cliff in the Grand Canyon. Okay, so these are logically equivalent. Again, that's not a proof or anything, but we're not. I mean, these are all things that are, you know, sort of assumed things, right? In some sense, these are tapping into your knowledge, and you could do a truth table for it and check it if you want. Okay, these two things have the identical truth tables. If you really feel disturbed by this, but probably you won't. Okay, and so then we also have A if and only if B. Okay, and by the way, there are also implications that so this A implies B, that's another way to write this, and this one is written A equivalent to B. So this means both A implies B and B implies A are true. So that the example of the jumping off the cliff, it's not an equivalence. Jumping off a cliff is not equivalent to dying, okay, right? You know, sitting in here is equivalent to being enrolled in Math 307, assuming that we have perfect attendance today. But that's not actually true for Math 141. If you pick a Math 141 classroom, it is not true that being enrolled in Math 141 is equivalent to sitting in that classroom. What's the difference?
There's more classes. There's more sections.
More sections. There's only one section of 307. So you're in here if and only if you're enrolled in 307. Take a 141 class. If you are sitting in that class, you are enrolled in 141, but it is not true that if you are enrolled in 141, you are sitting in that class. Okay? So that's the difference. All right, so you know, these are things that you just have to absorb, right? And they have to become a part of your language and your thinking. You have to build this special wiring, and your little logic conscience has to get developed so you feel nauseated when you make a mistake. Unfortunately, it's not infallible, okay? Sadly, the little, you know, I mean, you don't, you know, I mean, even I, you know, every mathematician and every math student occasionally makes mistakes and thinks, yeah, I got it. And oops, no, I actually, you know, okay, on second thought, no. Okay, so. But hopefully that happens in very, very complicated situations and not in very simple situations. Failure is a part of doing mathematics, sadly. Okay, but that's what makes it exciting, because every now and then you get it right and just, yeah, I braved all this stuff and I toughed it out, and yeah, now I got it and now I feel great. Okay, so. Okay, we have some more undefined things. X is, that means X is an element of A. They teach this stuff like in elementary school or middle school or something now, right? Okay, and of course I can't define this again because we got to start somewhere. I mean, I can say, well, that means that this thing belongs to that set. Well, then what is this thing set? Okay, but you all know what it means. Basically what I just said, that X is in this particular set. Okay. Mathematics and basically all knowledge, everything we do has to start with things that are undefined. Okay, so, and fortunately mathematics, we don't have a whole lot of them, okay? Set, element of, and they're also pretty basic things that will make sense to you. And the other advantage of not saying exactly what a set is, I mean, I can't, but it also allows me to say, well, a set can mean you know, a set of numbers. It can mean a set of rabbits, right? It can be a set of stars. It can be a set of lots of things. And all the things that I prove about sets are going to be true whether it's a set of rabbits or a set of stars or whatever, right? All the theorems I prove, everything I do works no matter what kind of set I'm talking about. And that's the advantage of not being, you know, I mean, you have to, but it's also an advantage of not being able to define exactly what a set is. Because we know what it is, we know when to apply it, and it works, right? It works. Strange, but true. And of course, you know what this means. I mean, I've already talked about these things, right? That just means that x is not an element of A. And if this stuff, you know, interests you, you know, there's all kinds of deep, you know, logic and things that get really to the heart of what all this stuff means and reducing the number of undefined things and so on and so forth. But if you're a more practical, pure mathematician like most mathematicians, if that makes any sense, you don't bother with such things very much, okay? They just annoy. Okay. So we have various operations that we want to do, probably many of which you've seen before in some form or another, like in a Venn diagram. So we want to discuss union, intersection, take away, and, oh, one more before that, subset and empty set. Okay, so let's start with union. Now, I think probably all of you have seen Venn diagrams before at some point in your life, right? And, okay, and so how do I draw, if this is A and this is B, what's the union of those two things?
A and B, right?
Okay, and I'm so glad you said that, okay, because he said A and B. So you shade A and B. Okay, now this is not useful for a proof. It's useful for ideas, okay, but a proof, you have to sit down, you have to talk about what's in the set. So what we're going to do is we're going to use set notation. So, and you've probably seen this before in calculus, right, or at some point. It's the set of all x such that, sometimes you will see a bar, and I don't care which one you use, such that, and now you describe the properties of x that put it into the union. So I'll get started on it. It's x, an element of A. Okay, but that's just this, right? So how do I go from here? Oh, I heard a different word. Okay, so I heard and down here, and I heard or over here. And we know they're very different. Well, and or isn't something we defined in here. That and or is actually just or, right?
Yeah, because it's both.
Right, because or allows it to be in both. Okay.
Wait, it can't be and because that would be like the intersection, wouldn't it?
Yes, okay. So, but here's the thing. How do you make the Venn diagram? To make the Venn diagram, you shade this and you shade that.
Yeah.
Okay, well here's the difference. In the one case, you're talking about how to make a Venn diagram, okay? But what's important to us is not the Venn diagram, and that's useful, but what's important to us is what is the property of x that puts it in this set, because that's what this kind of definition is used for, right? And later on, when you're doing proofs of this, you're going to have to pick up an x and say, oh, it's in here, and then you're going to have to write down what it means for x to be in there. So I heard somebody say correctly, but so or x an element of B. Okay, now let's just check that this actually does correspond with the picture, even though in the picture someone described it using an and it can correctly be described, right? That is what you do. You shade A and you shade B. Okay, but that's not describing what an element in there looks like, okay? So let's see if this is true. So x an element of A or x an element of B. Well, let's see. Well, we got shaded in here. Well, if x is right there, then what? It's in A. So this definition is correct. If it's over here, it's in B. So it's still in the union. What about if it's here? Well, that's our and or, okay? But right, that's basically just or. Yeah, it's in A, or we could also say it's in B. Either one, we got our choice. Okay, but it's still true. And likewise, so what I showed that if you're up here in the shaded region, then the definition is satisfied. That was really only a one way, right? I mean, I want to show this is equivalent. So let's suppose I look at this definition and pick up something in here and make sure it's in the right place in the picture, okay? So this says we got this condition, we got that condition, okay? So let's suppose X is in A. Where does it go in the picture? Let's erase these for now, right? If it satisfies this definition, where does it go in the picture? If it satisfies this one, where does it go in the picture? It goes in that part. If it satisfies this part of the definition, it goes in that part. So this correctly describes the Venn diagram. Okay? So somebody already observed this, right? The intersection is a set of all x's, x is in A and x is in B. And if you look at this picture, is that going to be in the intersection? No, because it has to satisfy both conditions. It has to be in A and in B. It's in A, but that's not enough. Okay, likewise, something over here isn't enough because it's in B, but it's not in A. The only options are those things there. Yep, the intersection. So that is the intersection. So the words connected with these are union and intersection. Yes. Okay? Questions about those two guys?
And the symbol for is a caret, the, you know, for or and and.
Yes.
They're
So
opposite
right.
directions of the.
No, they're not actually.
Because
They're not.
or-
This is or is a
points
V.
to the ground.
Yep,
Yeah,
yep,
yeah,
yep.
yeah.
Okay, and we're not going to use the logic symbols very much in here. You're welcome to do them yourself, but I don't want to load, you know, I'd rather just continue to use the words. It's not that much more complicated, okay? So, but yes, the or symbol is a V, and that's not a coincidence, okay? I mean, there's a 50-50 chance of it working out, but I think somebody planned it that way, so, right, okay, so. All right, so let's look at A. Take away B. This one is only slightly tricky, but let's see. It's a set of all, and let's maybe put a Venn diagram over here. So here's A, and here's B. What should it be in this picture?
All of A but not B, so.
Okay, so good. All right, so it's going to look like that, right? A, if you A, take away B, that's how you read that, right? Then it should be, now, okay, so what you just said, and I don't know your name yet, but anyway, the last one wasn't right, but now this one is, okay, so that's good, right, making progress. So thank you for saying that. So now, can you tell me what to write here? It's basically what you just said. Such that X what?
Such that X is an element of A. And we don't want to use not.
Actually, in this case, we can, yes. I mean, that's when we're negating things.
Right.
We don't want to leave the knots around here, but we have a legitimate symbol for that, right?
Right.
So what's going to combine, and some of you know, I know, but just we'll let them struggle through, okay? See, you speak up and I torture you in front of the entire class, right? So, no, but you learn, okay. So, so what do you go ahead and use the not. What is it you want to have here?
Not an element of B.
Okay, but we need to connect these two things. So which conjunction are you going to use? You actually said it correctly.
And?
Yes. It has to have both, 1 second, Sarah. You have to have both conditions. It has to be in A, and you could say but really you want to say and it's not in B. Okay, so question.
Just a technicality, does it matter if it's a backslash or a forward slash?
You've been studying computer science, right? Okay. No, I mean, all of you do this in your, yeah, right. I mean, this is not a question that would have been asked, 15 years ago, but okay, now we all use, now it makes a difference. But yeah, I mean, if you do it the other way, there's something called a quotient of sets, and, there are things that, so anyway, it should be backslash, but I'm not going to beat you up if you do it the wrong way. I'll just say, well, you should flip that over. I'm not like your computer, which will really, get upset if you get it backwards, okay? So, yeah, but that's the way it should go. Some people just do this, right? But the danger of that is that, well, the danger is that when you think about this, you think of, well, I don't know.
A minus
A
B.
being, yeah, A minus B, and you think of B being sitting aside A. And in fact, I'm going to bypass this one and skip right to here because, oh, we're almost out of time. Okay. What if I have this situation? What is A take away B? Well, to answer that question, you go back and look at your definition. That's the handy thing about definitions, right? Whatever you may think it is when you first look at it, the thing that matters is the definition, right? And so it is a set of all x such that x is an element of A and x is not an element of B. So what is that? That's just A. Now in this case, it equals A. And what is, in this case, A intersect B? It's what? In this picture. Okay, but there's a special name for that. That's the empty set. The empty set is a set with no elements in it. It is a thing, okay? It is something that you will have to deal with. It's not nothing. Okay, which is kind of funny. I just last night saw the movie Dead Man, and there's a guy called Nothing in there. So anyway, yeah, so it's not nothing. It is something. It's the empty set. It's the set with no elements. So that's a good stopping place for now. Next time we'll be discussing the relationship between these further, and we'll be talking about subset and